Have you ever looked out at a rainy day, maybe here in Columbia, Missouri, and just sighed thinking, well, so much for solar power today?
Yeah, I mean, rain's usually the enemy of solar panels, right? Stops production.
Exactly.
Mm.
But what if, and this is pretty cool, what if there was an innovation that actually turns that rain into, well, an opportunity?
That's precisely what we're diving into today. We're looking at rain-powered solar for Columbia, Missouri, a dual-function approach.
Okay.
So our mission really is to unpack how this cutting-edge tech generates electricity from both sunlight and, believe it or not, rain.
Both.
Yeah, and we want to see how relevant it is for a place like Columbia, look at the economics and, the unique advantages.
And we're basing this deep dive on some really fascinating bits from a Black Knight Power white paper. I'm honestly excited to get into how you use something as common as rain to make power. It kind of flips the script.
It really does. And I'll be walking us through some of the science behind it, the mechanics, but also stepping back to see the bigger picture, why this matters.
All right, let's unpack it then. How on earth do these rain-powered solar panels actually work? It sounds almost, well, impossible.
It does sound counterintuitive, yeah. But what's interesting is they start with traditional solar panel tech, the photovoltaic stuff.
Okay.
But then they add a crucial layer, graphene.
Ah, graphene. Heard a lot about that material.
Yeah.
Super thin, right?
Exactly. A single layer of carbon atoms, incredibly strong, conductive, unique electrical properties. So when raindrops hit this special graphene coating, the ions dissolved in the rainwater, even tiny amounts, they interact chemically with that graphene surface.
Oh, so it's not just the, physical force of the drop hitting it. It's chemistry.
Precisely. It's not kinetic energy we're capturing here, not primarily. It's a specific chemical exchange. It's called a Lewis acid-base reaction.
Lewis acid base. Okay, pulling out the chemistry textbook there.
Sort of. But think of it like a subtle dance. Electrons being donated and accepted between the water molecules and the graphene.
Right.
And that dance directly creates an electrical potential difference.
Yeah.
Voltage.
So you're tapping into chemical energy when it rains.
You got it. Transforming those low sunlight, rainy periods into active energy generation time. Now, it's worth noting, these panels are less efficient in full sun.
Oh, how much less?
Around 6.5% efficiency compared to, say, 22.5% for good traditional panels.
Okay, that's a fair difference.
It is. But their ability to work when it's raining gives them this unique sort of continuous energy advantage that standard panels just don't have.
Which brings us to Columbia. The white paper mentions we get, about 38.5 inches of rain a year? And that might even go up.
Yeah, projected to increase to maybe 40.7 inches by 2050. Plus, we have a moderate risk of those really heavy downpours.
But does that make Columbia a particularly good spot for this tech?
Well, connecting the dots, yeah. Columbia's climate, with that frequent rainfall, makes these panels make a lot more sense, doesn't it? It turns what's usually a downside for solar into, well, an upside. An asset. It also makes you think about designing energy systems for more variable weather in the future.
Okay, but let's talk brass tacks. Cost.
Yeah.
New tech usually means expensive tech. Graphene isn't cheap, is it?
That's true. It definitely increases the production cost. The white paper estimates like a 5-kilowatt system. The base cost is around $14,181.
Oof. Okay.
But wait, there are incentives. Federal tax credits bring that down to roughly $9,927. And then here in Columbia, you've got local rebates too. Columbia Water and Light offers, I think, $625 per kilowatt.
Okay. So that helps chip away at it further.
Right. So the paper projects that a 5-kilowatt system could potentially pay for itself in about 10 years.
10 years.
And over 20 years, the average savings could be around $12,920.
That's pretty compelling. What are the big ifs in that 10-year payback, though? What assumptions are baked in?
Good question. It assumes, energy prices stay somewhat stable and, crucially, that those federal and local incentives stick around.
Right. Policy can change.
Exactly. So yes, the initial cost is higher, no doubt. But the long-term picture, especially with help from incentives, looks pretty viable. And like any new tech,
Costs should come down over time.
that's the usual trajectory. As manufacturing scales up and improves, costs tend to fall.
Now, the white paper also mentioned something else interesting. Pairing this with rainwater harvesting. A dual function.
Absolutely. That's where it gets really synergistic. There was a case study, I think it was in Jordan.
Yeah. What do they find?
They tested these dual-use panels, solar generation plus rainwater collection, and they managed to collect up to 444 liters of rainwater.
From how big a panel?
Just a 4 square meter panel area. And that was over only 2 months.
Wow, 444 liters. That's not insignificant. That's a serious dual benefit, power and water.
Exactly. It really broadens the whole sustainability discussion, doesn't it? For Colombia, imagine maximizing utility during our rainy seasons, getting energy and collecting water simultaneously.
Addresses two resource needs at once.
Right. It makes it a really compelling option, diversifying the city's renewables while tackling climate challenges like water scarcity, potentially. It shows how local policy, like those rebates and innovation, work together.
Okay, so let's wrap this up. What are the key takeaways for you listening?
Well, first, Colombia's climate, with all that rain, makes it a potentially ideal spot for this tech. That 38, nearly 41 inches projected really matters here.
Right, and the core tech itself using graphene and that Lewis acid-based reaction, it's genuinely innovative for getting power from raindrops.
Then there's the economics. Yes, higher upfront cost for, say, a 5 kilowatt system, but after credits and rebates, that payback hits around 10 years, potentially saving over $12,000 across 20 years, and costs will likely drop.
Don't forget that dual function, combining the rain power with actual rainwater harvesting. That Jordan study showed real potential, hundreds of liters collected.
A powerful synergy.
Definitely. So it leaves us with a thought, doesn't it? Considering how these kinds of innovations try to leverage all the natural resources available, sunlight and rain, what other maybe overlooked elements in our environment might hold untapped potential for future sustainable solutions? Something to think about.